So let's talk about systems of linear equations in two variables. My two variables could be anything, but again, following our tradition of using variables with letters from the end of the alphabet, we're going to use x and y. I'm also talking about linear equations, so you know there's not going to be any squares or anything, it's just going to be x's and y's. We're talking about systems, and that means I have more than one. For every unknown you have, here I've got two, you're going to need an equation. So since I have two variables, I need to have two equations that I'm dealing with to solve this. First, I want to talk about solution methods. There are three solution methods, and so here's the trick to making this section work for you. I've got two sets of threes. I'm going to have three types of solution methods. I'm going to have three types of answers. The first solution method is called graphing. These are just linear equations. You can graph them and see if there's a solution. The other type we call substitution. You solve the equations and then you substitute one into the other. And don't worry, I'm going to work through examples of all these. And the last one is called addition. You add the sets of equations together and then you find out your answer. Let me go through just a second what some of the pros and cons of these might be. The graphing thing's a little bit crude. It's unwieldy. This is because, as you can see from my writing, I'm not really a good artist. I don't do well with graphing, particularly if we're trying to graph things and get answers like, 3.61 or something. That would be very difficult to get. A nice whole number you could probably get out of this. But other things, it's a little bit difficult. Still, I talk about graphing not so much that I want you to do it, as it is going to be useful in seeing what my three possible solutions are, because we'll be able to talk about pictures. So always go back to graphing. Graphing, a picture's worth 1,000 words, that's true. So this is nice to look at. Good for looking at. That's a pro. Substitution method. This is very algorithmic. An algorithm just is something where I have a very specific process that I can list out the steps for you. Algorithms are used a lot in computer coding to make sure that you have a good high-level understanding of what's going on. Algorithms are great. It's a process. Anybody can follow an algorithm. The downside to algorithms is that they're a little stilted. They're cumbersome, overly formal. So algorithmic can be good in that there's no way you can mess it up, but this is a bit of a pro. We don't like things that are cumbersome. The addition method is very efficient if used properly. As a comparison between these two methods, think of factoring as a lot like the addition method. I'm not saying we're going to factor in the addition method. I'm saying that the addition method is like factoring. If you can see how to pull apart a quadratic equation, then factoring's faster. Think of substitution more like the quadratic formula. It's always going to work, but you don't really want to deal with square roots if you don't have to. Okay. So having given these three types of solution methods, let's talk about possible solutions. Remember, we're talking about linear equations. So, if I'm talking about linear equations, there's three possible types of solutions, and I tell you there's three solutions. We can look at these things. If I'm talking about linear equations, that means I can graph them. So let's pretend like we'd solve some things using the graphing method. Remember, I've got systems of linear equations, two variables. Since I had two unknowns, I told you that means we need to have two equations. Each equation looks like a line. So here's one line. And now let's see what the other options are for my second line. Well, my second line could be parallel to this first line. They'd have different y-intercepts, but they'd have the same slope. My second line might be completely different. They might cross somewhere. Or my second line could be parallel. Let me make my first line just a little thicker so you can see what I'm really talking about here. Of course, lines don't actually have thickness. I'm just doing this so that it looks like something's happening here. Otherwise, I'd cover up. If that's my original line, my two lines could be parallel, and not just parallel, they could be parallel with the same y-intercept. If these happen, what have I got? I've got two parallel lines here, but they have different slope. In terms of finding a solution to this system of linear equation, these two lines never cross. They have no solution. If I solved them using the graphing method, I would just see they're two parallel lines that never crossed. But again, I said the graphing method was a little bit unwieldy. So if I'm solving it through some other method, here's how you can recognize it. You're going to get something untrue, something like 2 equals 0, 3 equals 4. Just like if you were solving equations, and we talked about equation solvings, when they had no solutions, they would give you these math lies. Well, if you try to solve a system of linear equations and they're parallel lines that have different slopes, you're going to get the same sort of mathematical lies here that don't work. This type right here, here you have two different lines. They've got different slopes. Ooh, excuse me. I've completely lied over here. Not different slopes, different y-intercepts. Wow. On a scale of things I could lie to you about, that's probably like an 8 on a scale of 1 to 10. Different y-intercepts. My goodness. These guys have different slopes. The lines are completely different. This means there's one solution. And as a picture, we know exactly what that solution is. It's this little common point right here. It's the one place where the blue line and the red line match and meet. And we're going to know this is happening. Here's the sign that you can tell to look for it. You're going to have a solution where you have x equals some number and y equals some number. These are two blanks right here, and some number is going to get filled in. So you're going to be solving your equation, you're going to be using substitution or addition method, and you're going to have an actual answer here for your x and your y. And lastly, oh, it's super hard to see here, and I think a little bit of my graphics is going just a little bit messy. If I've got this situation going on, we once again got parallel lines. This time they have the same y-intercept. At least I've stopped lying to you now. This is what happens when I've got two lines, one on top of the other, and they have the same y-intercept. They're parallel lines, so they have the same slope. That's what parallel lines do. They have the same slope, so that's why that lie over there made no sense at all. And when this happens, we say they have infinite solutions. And one of the ways you can recognize this if you're solving them formula-wise, algebraically, is you're going to get something that's always true. 0 equals 0, 2 equals 2, 5 equals 5, something like this. Some mathematical fact that's just completely true. So these are the three different solution methods: graphing, substitution, addition. And these are the three different types of possible solutions. If you try to make two lines play with each other, this is the only three ways that they can work. So, having said that, let me go through and solve three examples. Each example I'm going to solve with a different solution method, and it's going to give me a different solution answer. Any one of the methods can give you any one of the answers. In real life, one method will usually be the fastest to get a particular answer depending on the equation. I'm just going to go do them in order of graphing, substitution, and addition. And it's going to give me, in order actually, no solution, one solution, and infinite solutions. Again, use whichever method you feel most comfortable with, or learn all three and use whichever one's fastest. Don't get stuck. And if you're going to pick one and stick with it, I recommend not graphing. Substitution or addition is going to be what you're going to do if you're only going to pick one. because graphing, like I said, it's a little bit unwieldy. It doesn't work for things that aren't whole numbers usually, because you just can't possibly, if you're trying to figure out where exactly these two guys cross, that's going to be difficult to do just by looking at a graph. So graphing's a little bit not so formal. All right, so let's talk about my first one. Here's what I've got. I've got negative 2x plus y equals 4. And I've got negative 2x plus y equals negative 1. This is my system of two equations. It's trying its best to have a little bracket here. I've got two equations that are linear, and I've got two unknowns, x's and y's. If I'm trying to solve this using the graphing method, well, here's what I do. I take each of the equations, and I solve it for y. So I'm going to add 2x to both sides and get y equals 2x plus 4. And I'm going to take this second one, solve him for y, and get y equals 2x minus 1. Then I'm going to graph these two. In a previous video, I think I already graphed the first one. 1, 2, 3, 4, 5, 6. And I figured out that it had a y-intercept at 4, and then I had another point over here at 1 and 6. So I had this on my graph. And then for my second equation here, I've got 2x minus 1. This is going to have a y-intercept down here at negative 1. And it's going to have another point up here. And it's going to be a line here. I can't draw all that well. My graph is not to scale, but the key point here is that these two have the same slope. And that means these lines are parallel. So the curves are parallel. And I'm using a symbol here for parallel. You've got double lines for parallel, and you've got this for perpendicular, which means some sort of right angle like you'd find on a wall. So I got the same slope, so the curves are parallel, and they have different y-intercepts. Different y-ins. So this tells me that there's no solution. Again, if I'd drawn my graph a little bit more to scale, I'd convince myself that no, these really aren't pinching together and going to cross somewhere up here. They're parallel lines. They're like railroad tracks. They're never going to cross each other. That's what no solution might look like. For my next set of linear equations, let's talk about 3x minus y equals negative 9 and 4x minus y equals 5. I'm going to solve this using substitution method. Substitution method says this. Pick one of the equations, step 1, solve for y or x. Plug into the other equation. This gives you a single equation with only one variable. Solve for the remaining variable. And then, once you've got that variable, plug that in into one of the original equations. This will let you solve for the last variable that we've got. So, substitution method, I've got no particular feelings on this, so I'm going to grab the first one. 3x minus y equals negative 9. I'm going to solve this for y or x because y is the number here, or y is the letter here that has no number in front of it. I'm going to pick solving for y. So let me add y over to the other side. 3x equals y minus 9. Let me add 9 to both sides. 3x plus 9 equals y. This is something that's equivalent to y, so now I can take my second equation, and I'm going to plug this first equation into the second equation. So let me do that. My second equation says that 4x minus y equals 5. I know what y is, though. 4x minus, I'm replacing y with what it is, 3x plus 9. And all of this equals 5. Distribute this negative through. 4x minus 3x minus 9 equals 5. 4x minus 3x leaves me with x minus 9 equals 5. And now I can add 9 to both sides and get x equals 14. And now here's the substitution part. Once we've got that, we've solved for the remaining variable here, which told me that x was 14, and now it's time to plug that remaining variable into one of the original equations. I'll pick the top one just because it's on top. So I have 3x minus y equals negative 9. 3x minus y equals negative 9. I plug in x equals 14, so I have 3 times 14 minus y equals negative 9. 14 times 3 gives me 42 minus y equals negative 9. And if I multiply both sides by negative 1, I'll get negative 42 plus y equals 9. And then I'll add 42 to both sides, so y equals 42 plus 9, y equals 51. This gives me my answer of 14, 51. And I think you can see from this answer that maybe we wouldn't have wanted to graph that, because to find that solution, I'd have to go over 14 spaces on the x side and have to go up 51 spaces on the y-axis, and that would just be rather messy. So that's substitution. And our last method of solving things, and notice not only is this substitution, but I've got a very particular answer. This is a one-solution process. If I had graphed these two equations, they would have met up here at the point x was 14 and y was 51. There would have been two lines that would have crossed at that point if I did graph them. Again, because of this 51, maybe graphing would have been a little messy. My last method is the addition method. The addition method, again, is most effective when I've got something that is very easy to see what's going on. And here's the addition method. Here's my initial set of equations. I've got the equation of 2y minus 4x equals 8, and maybe y minus 2x equals 4. For the addition method to work, I need to have a y's column, an x column, and then I need to have a constants column. It doesn't really matter which side of the equal sign they're on, but they have to be on separate sides of the equal sign. Here's the trick to the addition method. You write your numbers out, and then what you do is you look for a way to get two things to add together and cancel out one of the columns. So I notice here that this, in front of this y right here, there's of course a positive 1. If I multiplied the bottom equation by the number negative 2, then I'd have 2 plus a negative 2, which is 2 minus 2, and that would zero out my y's column for me. So for the addition method, you pick a number to multiply 1, and here maybe I'll get rid of this, one of the equations by. This wants to be something like a magic number almost. And here's what I mean by magic. The number must let you add the two equations together. EQNS for equations, equins as an abbreviation, two equations together, so that one column cancels out. This is the big thing. So that one of the columns cancels out. So if my first equation was 2y minus 4x equals 8, and I chose to multiply my second equation by negative 2, first I have to distribute that negative 2 on the left, so I get myself minus 2y. Negative 2 times negative 2 gives me positive 4x. And then if I multiply by negative 2 on the right, That's going to give me 4 times negative 2, which will give me negative 8. Then you add these together, column by column. 2y minus 2y gives me 0 for the y column. Negative 4x plus 4x gives me 0 for the x column. And 8 minus 8 gives me 0 here. If this had been the type of equation that was going to give me one solution, I would have canceled out the y columns and I would have just had x's and constants left that I could solve. But this equation tells me 0 equals 0, and this is the pattern we talked about for solutions where I had infinite number of solutions because these were really the same line. If I had a graph of these two lines, they would have been both doubled up over each other. Since I got this, I know that my answer is infinite solutions. They may have looked a little different when I wrote out these lines here, but in reality, these were really the same two equations. And there wasn't a difference between them. This equation is just this bottom one multiplied by 2. And that doesn't change what the equation looks like. Again, that made me a little dizzy. Any of these three methods can be used to solve get any of these three possible solutions out of. If you're going to just pick one solution method and go with it, I recommend one of these two. In particular, I would say if you're just going to pick one, substitution is probably your friend. But remember, it's cumbersome. It will take you a little more time. When I'm writing exams and such, I do try to write them so that there's about for 50-minute exams, I try to write them so they're about a 35-minute exam for a well-prepared student. Part of that well-prepared aspect would be that you would use the fastest of the three methods. So if you're going to pick substitution, that's the most powerful, I would say, because again, it's algorithmic, but it leaves yourself open to some risks, maybe, of being a little bit slower. Anyway, this is an infinite solution one. So now you're ready to tackle systems of linear equations in two variables and use the most effective solution system possible to get no solutions, one solution, or infinite solutions.